Hi, friends of the sun. Welcome to our weekly reading group happening every Monday. And if you want to join it yourself, all the stuff for that is down in the description. And today we're talking about a paper where the people have a language model for generating protein structures and doing that autoregressively instead of with diffusion models like basically everyone is doing these days. So let's see how that works.
I'm Ben Murrell from Stockholm at Karolinska. And just to introduce myself and my lab, we're historically kind of an interdisciplinary lab. And then in 2020, because of the pandemic, we just became a wet lab almost entirely uh, until those projects started winding down. And we wanted to get into something a bit more computational, but we kind of enjoyed getting scooped twice a month, every month. So we thought protein design might be a fun field to go into because it seems nice and active and competitive. And I should make it very clear that the front three authors on this have really carried this project. So that's Lucas, Anton, and Aaron. I think they'll mostly be on the call. I might bounce some questions to them if necessary. I'm also happy to be interrupted, so feel free to just pop up and ask as I go along. That's not a problem. Yeah, so I'll give an overview. I'll briefly mention current approaches. I'll talk about our autoregressive formulation and then go through the details. I'll talk a little bit about how the model behaves. It's obviously still very early for this, and then talk about some next steps that we're interested in. And I'll mention a little bit to proselytize for working in Julia because we think it's quite a nice language to work in. So the sort of approaches that are that have the most sort of standing, I think, are initially this deep network hallucination, which you take a folding model and you optimize a sequence or some sort of soft representation of the sequence to maximize some metric of confidence for the folding model, and you use that to design a protein. And there's a few approaches in that space, as far as I can tell. And then this might be offensive to some people, but I'm going to bundle diffusion and flow matching approaches together because they both have this shape where you train a model to effectively denoise a noised structure, where the noise is kind of indexed from very little noise all the way to pure noise, and inference steps from pure noise down to no noise. But the key feature of both of these sorts of approaches is that they're holistic. At every step, the kind of the current version of the solution is being tweaked and updated, and we wanted to ask, can you do it not like that? Can you design a protein backbone just like a large language model samples text? So one amino acid after the next, where when you place an amino acid, you're committed to that placement. So that was the sort of central thing, and it doesn't seem to be a completely it seems to be something that I'm sure people have considered, as you were saying. So just there's a bit of a running joke that diffusion papers are quite hard and large language model papers are quite easy. So this is very much a large language model paper in that respect, just to calibrate your expectations about the sort of technical difficulty here. But to state the problem, right, we want to generate backbones autoregressively. So that means the input must be the backbone coordinates and the amino acid sequence so far, and the output must be the backbone coordinates and the amino acid for the next residue. So you're going from, let me actually just make this a laser pointer. You're going from here and you've seen everything so far and you're adding one more residue frame, right? And I'm going to just drop the consideration of the amino acid. Right, I'm just going to talk about the coordinates because the amino acid is a discrete character. We all know how to do that autoregressively. Now, it turns out this has actually been done before, right? In this paper in Nature Communications, with a very similar rationale to us. So this approach is conceptually similar to causal language modeling, with the important difference that the inputs and outputs are continuous values rather than probabilities over discrete tokens. Right, and so this is an autoregressive model. It uses masked attention, and it optimizes an L1 loss against the angle that it emits and the true angle. right? And that model exclusively produces alpha helices. It just makes helices. That's all it does. And I just want to clarify that I'm not dunking on this paper. This was not at all the central point of this paper. This paper was about a diffusion model, but it's really instructive to know that when you optimize the autoregressive prediction of the next frame in the sense of a point estimate, what you do is you just produce alpha helices. And the thing that's missing from this is the stochasticity. Yes, sorry, is that a question? I can't tell if you're
Yeah,
putting
I
it.
basically wanted to ask about that. I think like what did they look into like high temperature or low temperature sampling for that and how that affects whether or not you constantly produce helices?
I think if I understood that, so we kind of saw that paper as we were writing up, right? We hadn't seen it before, so I haven't looked at it maybe quite as closely as I should. So you should ask them instead of me. But my understanding is that they don't sample; they just place according to
Oh,
it's a deterministic output, right? So there's no temperature, um, and that's why this loss is an L1 loss. There's no distributional uh, output here.
okay. I thought it was like a diffusion model.
No, so it's just to clarify that that paper had a diffusion model in it, and this is something that they trained as a comparator in autoregressive,
Ah,
uh, one token at a time. But
okay.
they had an L1 loss on the angle instead of a distributional output, right?
Yeah.
So the key thing that's missing, as you understood, was the distribution, right? You can't just place an angle with your best prediction as a point estimate. You have to match the distribution over possible placements of the next residue, and then you can sample from that. So it's that little bit of stochasticity in the middle there that was missing from the previous thing. Um, Right, so our input is a backbone coordinate so far, and our output is a distribution over the backbone coordinates for the next residue. So what does that actually look like? We need to place 3 atoms, a nitrogen, alpha carbon, and carbon. So that's 9 degrees of freedom. The standard one very standard representation for this is in terms of dihedral angles, bond angles, and lengths. And this has a really nice inductive bias because the bond angles and lengths are relatively close to some ideal value, and the dihedral angles are, they capture the majority of the variation. We would like them to capture all of the variation. We don't want to deal with these Newsets bond angles and bond lengths. And it was actually similar in the previous paper. They also considered this. But if you just set the bond angles and bond lengths to the ideal values, you're kind of locally fine, but you get an accumulation of errors across a long sequence that can cause quite large structural deviation. So if you think of a sort of peptide folding back on itself, little angular accumulations can make the thing, completely clashed or completely separate after they've accumulated enough. So instead of just fixing them and picking and choosing which ones to fix in a way that doesn't break things, too badly, we first idealize the structure in the sense that we make small adjustments to the dihedral angles until the bond lengths and bond angles are all at their ideal values, and you effectively have no accumulation of errors. So your structure looks exactly the same. If you zoom right in, you get small deviations in individual atomic positions on the order of 1/20th of an angstrom, and your TM scores, if you look at the scale, are all really, really close to 1. And now the only variation in the protein is the dihedral angles. Yes, go ahead.
Can you explain a little bit how you do this? Like you, right? And sometimes we have bond lengths that don't correspond to the bond lengths that we like, usually see. And so now you just, in your training data, change that and pretend it were the bond length that you usually see, and you adjust it by, like make sure that the structure still makes sense by adjusting the torsion angles. But how does
Yeah.
this procedure work?
So basically, there's sort of 2 cases. The one is when your bond lengths look like they're from, like they're close to the ideal value, like they're in this sort of peak here. And the other is when they're kind of broken for some reason. So we catch the cases where they're broken and we treat that as a new frame, right? So if it's a huge departure from what the bond length should be, then there's something wrong in the structure. It's either missing residues that shouldn't have been missing, or something like that. So we kind of reinitialize the next frame and we mask out the dihedrals for that case. But when the bond lengths or bond angles are kind of within this tolerated window, the procedure is to basically take gradient steps on the atomic positions to make these bond lengths and angles go to the idealized values exactly, and that implicitly changes the torsion angles to compensate. And it turns out you can do that basically in all cases, as long as you don't have breaks in the chain that you're not aware of, as breaks, if that makes sense. Okay, happy with that explanation. Okay. Yeah, so we do that to all of the training data, and now the only thing that varies is the dihedral angle. So that's the only that we have to model 3 angular degrees of freedom, right? So the problem statement is now we have the backbone that we've seen so far, and we want to place a distribution over our 3 dihedral angles, and we say, whatever we do, some network will produce some embedding, some vector that captures everything so far. And so we have to model a conditional distribution of 3 angles conditioned on that vector. And we factorize that. So we have the product of 3 univariate angular distributions. And when you're generating over one angle conditioning on some other angles and this vector, we just featureize the other angles that we've already seen so far and concatenate them into the vector. So the whole problem is just modeling the conditional distribution over a single angle given a vector that's kind of telling you what the angular what the distribution over angles should be. And then the sort of trick we use is to get the neural network to directly emit the distribution parameters for a complicated enough distribution to handle a single univariate angle. And if you think about it, in a large language model, that's exactly what the logits over the tokens are doing. They're just controlling the probabilities, which are parameters of a distribution directly. So this is just exactly the same as that, but over the continuous case over angles. And our particular setup for that, you first have to choose a distribution over angles to work with, and then we construct a mixture of those. So a particularly nice distribution over angles is the von Mises. It's log PDF. You can think of it as a planar slice through a cylinder, right? So it's really, really simple. And its sort of standard parameterization has an angular mean and a concentration parameter, that when the concentration parameter is 0, it's uniform, and when the concentration parameter goes up, the sort of slice through the cylinder log PDF changes its angle and becomes steeper, and that corresponds to the density becoming more peaked in the direction of steepness. But if you
what do you mean with the slicing through the cylinder? Is it that that sort of the area, no, not like the circumference that your slice now has corresponds to the density or something like that, and that's the like the angle of the slice? And yeah, no, I don't.
I should have had an image for this, so I don't have to wave my hands. But it's literally, if you just think about a cylinder as being, an extrusion of the circle that your angle lies on, a planar slice through that cylinder is the log density of your angle. So if you take that and exponentiate it, you get the shape of the actual distribution over your angle.
Okay.
So it's just it's a very easy object to work with, because you're really just controlling the sort of angle of this plane that's cutting through. And then obviously there's a normalizing constant that depends on the concentration parameter, but that's fine. But having a network emit an angular direction is not a good idea, because you're going to have this discontinuity, and you kind of want everything to be nice and smooth. So we reparameterize this. We're not sure if this is a standard trick or not, but it's not very sophisticated. But you're basically just reparameterizing, instead of having an angle and a concentration parameter, you just have a point on the plane that kind of controls that angle of the planar slice through the cylinder. And then your log density has this really convenient form that can just be expressed as if theta is the angle that you're evaluating the density at, it's just the dot product of your angular mean and cos and sine of theta with some scaling. So that's a single von Mises distribution that's been reparameterized in this way. Now it's really nice and smooth because you can move this sort of point around on the plane, and as that point passes through zero, the distribution becomes uniform and can pass out the other side. So it's there's no weirdness in that. There's no discontinuities. It's a good thing for a network to emit and to train against. So we set that up as a mixture, right? You can't just have one of those because you might have many modes in the distribution over the angle that you're modeling, because the dihedral could send the peptide this way or it could send it that way. There's no reason to expect that to be unimodal. And how that looks is it's just a straightforward weighted sum of the density. So this is just visualizing that planar parameterization with the weights, and each of these points with its weight corresponds to the individual von Mises components over here. And then the model that actually gets used, the log density, is of this mixture distribution over the angle on this disk. And the architecture is you take an embedding vector and you pass that through a feed forward layer that emits the two sort of distributional parameters that govern where the peak is. And then you take the softmax of a third output, and that becomes the weights. And then that gives you your mixture density. So it's really just a little network that emits a flexible mixture density in a way that's nice to learn. So this sits for, you've got one of these over each dihedral in the sequence. That's, you've got a neural von Mises mixture over psi, then over omega, then over phi, each time concatenating the previous angle into the embedding vector as you step along. But it's the same thing every time. So that's kind of the newish trick on top of this. Everything else is fairly standard. I'm actually not too sure about this audience, but I assume people are quite familiar with AlphaFold setup and invariant point attention, so I'll be quite quick about it. But basically, one useful representation of backbones is as frames. When you standardize your bond lengths and angles, then you can, then every residue is just a, there's no variation within the frame itself, so it's an even better fit to this formulation. And what this lets you do is have a rotational frame for every residue, which lets you build an attention mechanism that can spatially reason about its neighbors. And that the key trick is, well, how it has a normal attention component and then an attention component that projects queries and keys spatially out into the global frame and looks at the closeness of the queries and keys. And when they match well, that increases the attention weight between those two residues. So we use that as the core sort of brain inside our layer. The thing that's doing most of the actual thinking here is this invariant point attention stack. But with one twist, because we want to autoregressively model this, we introduce an autoregressive mask. That stops any information flowing from later amino acids to earlier ones. That's completely standard. The one thing we didn't like is that invariant point attention uses softmax, which forces the attention weights to sum to 1, which forces the heads to attend to something, right? And in the normal AlphaFold use case, that's actually fine because you've got a lot of residues that you can attend to both behind you and in front of you. But when you have a causal mask, and you're sort of forbidden from attending to any residues in front of you, then imagine like residue 2, you're kind of forcing yourself to attend to only yourself in residue 1 with all of your attention, and there's sort of no way to suppress that. This has been used before in a couple of cases, but it's been popularized in this kind of like blog post recently. And this is especially bad in the setup where we don't have something like a start token. In a regular language model, you have a start token that attention mechanism can attend to, and that it doesn't have any semantic meaning. It can just be like an attention dumping way to kind of ignore all the other tokens. But because of IPA's equivariance properties, there's no way to build a start token into that, right? You have your first frame, that's all you've got. So the approach that's been advocated to deal with this is to use softmax 1, which is literally just adding 1 to the denominator of softmax. And that means that if the logits are low, you allow the attention weights to sum to something less than 1, right? So the network can decline to attend to something. There's a question. Please go ahead.
Yeah, no, it's a very interesting solution, and definitely helps with this problem that. The start token can be used to dump attention that should not happen, but I've also seen some papers arguing that having many start tokens, for example, allows reasoning outside of the tokens of the token space. But this attention sink, like softmax 1, does not allow that, right? It solves one of the issues, but doesn't for the other issues. So, you mind explaining why you can't just use an a start token, a empty frame, for example?
Yeah, the thing is that the frame has to be placed, right? So it has to have a physical location. So you have do you place it randomly? Do you place it it's just it doesn't have you don't have the same way to sort of decline to give it a semantic meaning as you can in a language model where it's just a discrete token. So yes, you could introduce like ghost frames that are not connected to anything else via their dihedrals and randomly place them and let them serve as attention sinks, or let them serve as some way of propagating information before things start sampling. It might work. It might be a good idea. It might improve things. But yeah, it still seems like even in that case, you want to allow a model to decline to attend to things. Maybe it makes a difference. Maybe once you introduce, prior ghost frames that have random locations, you don't need it. But yeah, empirical question. It's a good point though. Thank you. So okay. So the one little complication is that in invariant point attention, using softmax 1 actually breaks the equivariance. One of the steps in invariant point attention is you have frames emitting their values into 3D space, and those get transformed into the global frame, and then you take a weighted sum, an attention weighted sum over those values in the global frame, and rotate that back into the local frame of the residue. And these attention weights need to sum to 1 for this to be equivariant. The easiest way to see that is if you set all the attention weights to 0, which would be in the softmax 1 case if your logits were all really, really low, then all of this would turn into the global 0, right? And that would be not the local 0 of the recipient frame, it would be the global 0. And when that gets rotated back into the recipient frame, it would depend on where the recipient frame is relative to the global 0. So it would no longer be equivariant to rigid body transformations, right? But that also hints at the solution. You can take 1 minus the sum of the attention weights and multiply that, and basically include the local 0 instead. And so now it's you kind of it's almost as though you said, well, when your weights sum to less than 1, you will include a null logit that is the zeros in your recipient frame effectively, and then that restores the equivariance. So it needed that little tweak. But that's really all we do with IPA. So it's got the causal mask, it's got softmax 1, and it's got this little tweak to retain the equivariance for softmax 1. Our model stack is quite simple. We have sort of amino acid node features, and we have pair features. The pair features go into IPA. And we have this kind of weird setup with our skip connections and layer norm that's a bit non-canonical. Normally, you would either place your layer norm after the sum, or you would place your layer norm before the IPA. And we just found that placing it after the sum prevented us from scaling the model depth high. We'd kind of lose the earlier layers if we did that. And when we placed it before, it didn't work very well. So empirically, this is what we wound up with. It's got some weird behavior where you're now kind of normalizing the amount that you're adding into this, which is, it seems like an odd thing to do. And in later models that were kind of after the paper, we've played with balancing the scale to let us stack this even further, but we haven't really written any of that up yet. It's an IPA stack, layer norm, then skip connection, and then feed forward layer norm skip connection. That gets cycled n times, where in the model in the paper n was 12, and then out into the thing that emits angles. And now we've been ignoring the amino acids so far, but let's put them back. So what we do is it's exactly the same as how similar to how we model all of the angles. For a particular residue, you want to put a distribution over the first dihedral, then the second dihedral, given the first dihedral and the embedding vector, etc. We kind of do a similar thing for the amino acids, where we just pass the embedding out here through a feed forward and a softmax over the shifted amino acid. So this is now a distribution over the next residue's amino acid. And that log probability is added into the loss in training mode. And then that shifted amino acid is passed through, it's the one hot is passed through a linear layer and summed back into this embedding vector. So that means that the first dihedral angle has seen what its amino acid is going to be. And then, so the conditioning order is you take the embedding of everything so far, then you sample the next amino acid, and then you sample the three dihedral angles. We haven't played with the ordering there. This is just the only way we've set it up so far. And so, when you're sampling, you would sample the amino acid, sum that in, and then sample the dihedrals. The amino acid level features, we have the amino acid itself, one hot encoded. We have something that encodes how far you are in the chain. We condition on a sort of requested length. So we say, design something 120 amino acids long, and we tell the model at every step how many amino acid it's got left until the end of the chain, and a proportion of how far along you are. So it's just two different ways. And then the pair features, we have this, it's kind of like an IPA-like random projection and distances that just from the outset let the model have a sort of sense of the relative orientation and position of two frames, at every step. And we just encode this once, and it includes the differences in the residue index. So it can see how far behind how far behind a residue that it's attending to is, and whether or not it's in the same chain. And this all gets bundled into a fairly low dimensional vector and passed into IPA every stack, and it does not get updated. So that's kind of the whole model. For inference, we have two little twists. The one is, I'm sure you're all familiar with top P sampling in the discrete case. From this quite nice paper. You basically you sample from the region of high probability and ignore the tails, and we have a continuous variant on that we approximate with a stochastic reweighting of samples. And we've actually found that using different P in the top P sense for different dihedral angles can help. So we don't use the same sort of threshold for all the dihedral angles. We can be particularly aggressive with, say, omega, because it doesn't vary that much, and you have a lower chance of getting a bad draw and heading off in the wrong direction. The other thing that's kind of relevant for inference is these attention mechanisms when you have an autoregressive mask, you have a redundancy in your computation. You don't want to rerun the forward pass for everything every time, because then your sampling will be cubic. So we have a cached version where the n+1th amino acid kind of looks at the cached values for all of the 1 to n and sort of takes its output and adds that back into the cache. So every sample is order, if you're at residue n, you order n to do that sample. So your sampling overall is quadratic. That's a standard trick in regular large language models. Right, so that's the sort of model setup so far. Some notes about this. This was our first model. It's about 10.5 million parameters. It's 12 layers deep. Its embedding dimension is 196. It was trained on AlphaFold 2 predicted cath domains initially, and then on the full PDB. One thing that's quite fun is that when you introduce the nuclear sampling, the top P to throw away the lower probability regions in your angle space, about 18% of the time, it just decides that I'm a helix, which is, that echoes the version where you don't have any stochasticity. It only produces helices. If we take our nucleus P to the extreme value, it only produces helices. When you want to suppress some of those regions, it gets stuck in a helix mode. So it's a kind of mode collapse. But those are really easy to detect and discard. And the nice thing is that sampling is fast. So these are CPU sampling times. For this particular model, you can sample length 200 in about 5 seconds. So that's nice and quick. We haven't really timed GPU sampling, but it's it's very fast. Yeah. Any questions about the setup so far before I roughly walk through kind of our rather preliminary results on all of this?
Nope. Let's do it.
All right. So this is that model that we put in the paper. These are just 25 random samples from we followed that folding diffusion paper because they had a benchmarking pipeline that we just downloaded. So we kind of mimicked their length distributions and their metrics. And you can see nice, some compact domains, some kind of less compact domains, but pretty good secondary structure, decent helices, fairly high proportion of beta sheets. And when you quantify that, if you look at the sort of counts of helices and beta sheets, it follows a similar pattern to something that you see in like the AlphaFold 2 cath domains. Maybe a few differences down here, but fairly similar. If you look at STTM self-consistency, so if you refold, I think the folding diff pipeline uses omega fold. So this is, you generate 8 sequences using protein MPNN, you fold them all, and then you take the one that best matches, and you take its STTM. I think that's what that pipeline does. You get this distribution of refolding. So they're fairly designable. I don't have a whole lot of faith in these metrics personally, but that seems to be what they get called in the field. It has a fondness for making immunoglobulin domains. So this is a sort of similarity clustering plot. And most things are fairly dissimilar, but you can see there's a nice big square over here. And if you pull out the dominant component from that, it's a heavy chain immunoglobulin variable region domain. And it's very conserved everywhere except the CDR3, which has a lot of diversity. So this wasn't trained for this. This is just because in the PDB, I think immunoglobulin domains are overrepresented. So it's definitely found that mode, and it's fitting, maybe overfitting. It's not really clear when you start calling something overfitting, but that's part of its behavior. The other fun thing is you can visualize the attention scores for these sorts of models. So you can look at, as it's designing something, you can pull out a layer and look at the attention heads for the current residue and what that residue is attending to. And so you stare at these things for quite some time. And in this model, at least, that 550 model, there's one head in layer 7 that only attends like a couple of residues ahead while it's building a beta sheet. That's the only thing it cares about. It never attends to anything else. So sometimes the heads are doing something, incredibly specific, and other times they're quite diffuse, looking at lots of different things, kind of getting a sense of where the rest of the thing is. Not too surprising, but there's definitely specialization in these heads. And if you dig deeper, you can see things that will only attend to something else when it's a helix. And there's a lot to unpack there. But we're working on iterating the model, so we're not diving too deep into this specifically. I'll show you like a nice little preview of a new model that we've been playing with. So the previous one was 10 million parameters. We've been expanding the embedding dimension mostly to make the model larger. So we've shrunk each IPA layer in terms of the number of heads and values, and we've reduced the layers from 12 to 10, but we've dramatically increased the embedding dimension. And this is an 80 million parameter model. It takes like 3 days to train, to the point where it samples like this. And it looks like, we haven't run the metrics properly, but it looks like it's producing more coherent domains in its sample set. And at inference time, it's only twice as slow on the CPU, even though it's a much larger model. And it's just because the quadratic component is a bit smaller. So this is what we're tinkering with at the moment. And I'll show you these are attention visualizations from that 80 million parameter model. And one thing that's quite interesting is that when you blow the embedding dimension up, it's the proportion of diffuse attention heads actually seems to get larger. So some heads are specialized, but there's quite a few many more heads that are looking at lots of different things all at the same time. And that might just be because the model can, it's got much more flexibility in how it can transform the incoming values and do something interesting with them. So yeah, that's I spend way too much time staring at these things, trying to understand what the model's doing. So some sort of reflections on this. One of the current limitations, and that's something we're digging into a bit, is that the quality of the sample starts breaking down when the length gets greater than 150. And we don't know if that's just, the accumulated odds of making a poor decision in your placement when you're sampling placements randomly will grow as your sequence gets longer. So whether you can compensate by tuning the nucleus sampling parameters more stringently as you make things longer, or whether you need to occasionally, take a few steps back and resample, have a not entirely autoregressive sampling procedure, even though the model will still be autoregressive. We're digging into that. We also we've noticed some things about the keys and query behavior that we're looking into, whether it might be causing this sort of breakdown. So there's a lot of digging to do there. Another limitation is kind of like baked into this whole thing, is if you want to design a binder or something like that, the first frame needs to be kind of given. You can't place that under any procedure in this model for the, if you've got a target and you want to design your binder, you have to first pick an initial frame. Luckily, sampling's fast, so you could just randomly pick frames and generate things until you find something you like. So there are workarounds, and there's some more sophisticated workarounds we're looking into, but that's kind of inherent limitation. But thinking about this versus, say, diffusion and flow models, there's two things that I think might be important differences. So diffusion or flow models, they kind of have data augmentation built in to their training procedure, in the sense that for a single sample, you can see it many times, noise to different amounts, and each time it's noised differently. And so, you get many training samples that are all different from each other out of a single training sample. And this might cause it to be more economical with smaller amounts of data. And it might be the case that these autoregressive models need many more residue frames before they start behaving well, and maybe they're more prone to overfitting. That needs, I think, very careful investigation. And the other thing is that kind of more holistic methods that are always adjusting everything at the same time while looking at everything else, they don't have these premature commitment issues where you make one poor placement and then you paint yourself into a corner, or you can no longer pair with that beta sheet that would be really productive or something like that. So and some of the time it's only clear, like if you can think about designing a barrel, you have to make good choices very early on so that you line up at the end, and it's only clear that you've messed it up 200 amino acids later, and that's going to be really, really hard for the models to get right. So I think some of the challenges for autoregressive sampling are they might be quite inherent to this and quite difficult to get around, but it's still, we think it's quite promising for what it's doing for such an immature sort of model. So we got some next steps. We're going to look at the whole sort of bag of language model tricks. If you think about a language model like ChatGPT, you type in a prompt and it completes it. That's kind of what the binder design problem is in this sense. You've got a target, and once you get over the initial placement, that's the target serves as the prompt that you're completing from. And then there's a whole sort of collection of strategies to introduce more control over the designs. And some of those can get quite fun. The other thing is that this is an end-to-end differentiable sort of model of a backbone structure that is computed in quite a nice pass. And so there might be lots of ways to use that for other tasks. You can optimize the structure by taking gradient descents against this backbone probability. The other thing is, if you want to scaffold a motif, you can, it's completely trivial to train a sampler that can sample in reverse. And so around a motif, you can sample forward and in reverse and scaffold in that way. You can do in-painting, but that's much harder because the model has to make a series of sampling decisions that leave its endpoint really, really close to the starting point of some later frame. That feels like it might be quite challenging. And yeah, we'll see exactly to what extent these models can be trained to do that. Currently, we condition on the length, but you can also just introduce an end of sequence token and let the model decide how long something must be before it stops sampling. There's sampling under symmetry that requires some modifications from just the straightforward dihedral generation. You need to generate, evaluate in the context of the symmetry, and then kind of reweight your samples. And then there's a whole family of architecture variations that we're planning on exploring for this. Yeah, so we do everything in Julia, not just in this project, but in the whole lab. If you haven't played with Julia, it's great. It's a high-level language, but it's also fast. It has native multidimensional arrays, linear algebra. That's all fantastic. You never have to do anything outside of Julia, so it solves the two-language problem. And in the deep learning context, this means that you can do fairly complicated data transformations on the fly in your training loop without that becoming a bottleneck. And that's where this has been quite useful. Like if we imagine trying to do this in Python, there'd be things that we'd do that would just grind everything to a halt. It has a relatively mature deep learning sort of modeling ecosystem centered around flux.jl, but with a few other things coming out. There is occasional pain. So one thing we bumped into is that the layer norm layer, when it gets something very low variance, it just nans. And this was, took us embarrassingly long to figure out. But when you swap that out, suddenly everything in Julia's ecosystem just became completely stable. So if you've played with Julia and bumped into nans too many times, it very well could have just been the layer norm issue. It has some really nice auto differentiation. The autodiff system is decoupled from the modeling system because of Julia's composability. And one thing that also excellent is the package management, just the version control and the installing things just seems to always work these days. It's really, really good. So yeah, encourage you to play with it if you haven't. That's about all I've got. Again, as a reminder, Lucas, Anton, and Aaron are the leads on this. This actually this grew out of a summer school project. We run a summer school for high schoolers, and Lucas implemented invariant point attention in Julia as his high school summer school project, and then we kind of built this out of that, adding the modification.
Is which one need to require high pure score?
Not sure if that was a question. But yeah, we've got some funding from the Swedish Research Council and some GPU compute support that we've used a little bit for this, only for the big training run comparisons, like kind of like ablation studies, but not systematic enough to call them that. Most of this is just done on our little in-house A6000 GPUs. Yeah, so I think that's it from me.
Okay, thank you, first of all. And then I still have a little bit missing a notion of how this would compare in terms of the typical designability metrics to some diffusion models. Right? Have you any experiments where you use the same training data as one of those diffusion models and then looked at the designability?
No, we've kind of avoided comparisons with anything in the literature because we very much don't expect to be state of the art yet. Throughout development, all we did is looked at the structures, and then as it came to writing up the paper, it was like, well, we better run, at least one benchmark. So yeah, we definitely need to do more of that. We also need to familiarize ourselves a little more with what the state of the art for sort of benchmarks for these things are. It's a bit weird because the designability is premised on, I
mean, designability is a very contrived metric, right? This is not actually always what we want, or we don't always want high designability in every design task. It's just basically what we call designability is asking how well can AlphaFold fold this thing. And yeah, of course, this isn't always the best thing, but it's nice to, and right, it's designability. The way we've seen these papers now get high designability is by training on a data set that has highly designable proteins. And yeah, that's so even from that perspective, your model, even if your model was somehow super good in terms of generating super designable stuff, then probably because you train on normal data, so to say, you wouldn't get high designability numbers.
Yeah. If I could, I would do almost none of that, but we probably have to do some of it for publication. Because we're an interdisciplinary lab, I would get them looking right, and then I would start making them. I worry that, people have tried refolding, and they've shown that when things can be, when things are successfully refolded, then they tend to, express and fold to the target structure. But that could be, if you come up with a model that designs things that are distributed differently, it might be the case that you have poor designability, but your things still work in the wet lab. Or it might be the case that, that there's no reason to expect that the performance of designability as in predicting actual success in the lab to generalize to a different distribution of generated structures. So yeah, I'm not particularly concerned with those metrics. It's comforting to see things refold some of the time. Sure.
Do you have an idea, like an idea that we could use for evaluation to not just look at the stuff and see if it's, not just look at the stuff and see if it looks good, because that's kind of time intensive, and to instead put it in a number whether or not it looks good?
I don't have any better ideas than refolding it, but then, we'll think about it, but I don't expect it to do a better job than the rest of the field there.
Yeah. Would be very nice to have something new. Okay, cool. Then I suppose we also sort of have the questions. Yeah, have you tried something like doing scaffolding or so, or conditioning on some start snippets?
So it's trained to be able to do that in the sense that it has the sort of multi-chain information. I guess you're talking about scaffolding as in just initializing from a particular piece of something and extending. We haven't actually done that. That's next on the list, both that and multi-chain stuff, where we'll try and pick some design tasks where the initial, like the initial position of the second chain is kind of given for some reason, and then we'll extend that out. So maybe like diversifying a binder where you know roughly where it should start or something like that. So that's next in the list. My interest is always in trying to come up with those in a way, because if designability for single chains is hard to evaluate, designability for multi-chain tasks is a nightmare. So I'm always going to want to come up with ways where we can confirm whether it's doing what it should in the lab. And we're not quite there yet. We want to work on the models a little more.
And you also already mentioned that you can now you can do stuff like RLHF and DPO, but you can also, like, you have now this fully differentiable thing. And have you or what sort of experiments are you planning for that? Because I imagine that you could do something in the chroma direction now as well and generate proteins in the shape of letters, for example, or something like that. And
I think that'll be really hard because you
yeah, it would be a very hard energy landscape.
Yeah,
to
exactly. It's hard to see how you'd get from wherever you are now to shape like that. It'll be sort of canyons all the way. But the first thing to do is to, sample something and then try and optimize its global probability, which will let you make sort of adjustments everywhere. So you sample something that's imperfect in some places. Maybe a commitment decision over here means that this beta sheet is not quite right. But if you do kind of a global relaxation under this, you might tidy some of that up. So that's not doing anything new. It's just, it might be improving the designs. So that's where we're going to start first.
Yeah. I think actually one way that you might be able to get higher designability than other, like, even if that's maybe not so desired and not so interesting to you, but one way might be that you first of all train on the data sets that these maybe best 3 papers now with Genie, Multiflow, and FoldFlow 2 use, and then afterward you can do RLHF or DPO towards having higher designability. Right? You just fold a lot of stuff. You generate a lot of proteins. You fold them with AlphaFold, see which ones of your generated proteins have high designability, then do DPO with that. And then I would guess I think this might be a path to proving the designability metric wrong, or like really exploiting it.
Yeah, but so that feels a little bit more like optimizing for the metric than anything else, because
I mean, you're literally optimizing for the metric. Yeah.
I'll leave that for somebody else to try.
Okay. Oh yeah, that brings us to another question. Code, are you releasing that, or is that already released?
Yeah, so we kind of were getting the paper ready, and then the students had exams. So we kind of just got the preprint out before they went for the exams. We're working on tidying it up now. We've got a few components that are visible, like the IPA, but that needs it needs a little bit of tidying. 1 week, 2 weeks, depending on how quick we get things done, something like that. Yeah.
Nice. I think there might be lots of people excited to play around with it in this protein structure community. Like Alex Moorhead or something, I'm sure he'll do something cool with it. But maybe Julia will be a barrier to people doing stuff with it, but we'll see. Okay.
I hope it won't be. It should just install with a single line, and then it'll run.
Well, I know Python. I don't know Julia. To me, it certainly will be a barrier for playing around with it. Not that I don't plan to do it anyway, but if I were to plan it, then Julia would certainly be a barrier, even if it might be very cool. But then we also have maybe we can go for one more question in the chat, which I think fits the theme of the reading group. Could you re-explain a little bit again how you make your softmax 1 invariant? How you deal with the invariants?
Yeah, so Lucas has written a proof out in the manuscript. I'm not mathematically trained, so I just reason geometrically. So basically, the issue is that when your weights don't sum to 1, you're mixing in a portion of the global 0 into your into this term over here that gets rotated into the thing that gets concatenated into the outputs, and that global 0 doesn't come along with your frames when you apply a rigid body transformation. It stays behind, and now you lose your invariance. And so if you just take 1 minus the sum over your attention weights, so it's everything that didn't sum to 1, and you multiply and you sort of weight the local 0. So this ti is the ti of the recipient frame, and you sum that in. It's almost like saying you had something centered at your recipient frame emitting values of 0, right? And now you've got a mixture of your attention weights that don't sum to 1 and everything else, and the remainder of the sum and your local 0. And when you combine those together, everything will move, with your rigid body transformation. So that's kind of the intuition. If you want a proof, take a look at what we've got in the preprint.